So this is a problem session which is based on the 8th and the 9th week of this course. The assignment problems have already been given to you, and these problems are meant to supplement the problems which were given to you in the assignment. Hope you have done the problems in your assignment. So let's begin today by solving a problem on the diagonalizability of few given operators. So problem 1. So let V be the vector space P2 of R, which is the polynomial vector space of polynomials over R of degree less than or equal to 2, and let T be a linear operator on P2 of R. It's a linear transformation from P2 of R to itself. Then check whether the operator T is diagonalizable. It's diagonalizable when, so let's see, one is when T of say P of x is equal to P prime of x plus P double prime of x. P is sent to P prime plus P double prime. The second is, let's take some generic polynomial. It will look like ax square plus bx plus c. This polynomial is sent to, so this is by definition, cx square plus bx plus a. And how about the third one? Third one is just T of P of x is the evaluation of P at 0 plus the evaluation of P at 1 times x plus x square. Okay, so we'll check whether these three linear operators that's just given, whether it is diagonalizable or not. So let's start with the first one solution. Namely, P of x is sent by this operator to P prime plus P double prime of x. So I'll not bother checking whether T is a linear transformation. That will be an easy check. Rather, let's discuss the strategy which we will be using to decide to check whether T is diagonalizable or not. So when do we say that a linear operator is diagonalizable? We say that a linear operator is diagonalizable if we can get hold of a basis of V consisting of eigenvectors of T. But to talk about eigenvectors, we will have to talk about the eigenvalues, and eigenvalues can be realized as the roots of the characteristic polynomial of T. Now, the roots of the characteristic polynomial of T is the same as the roots of the characteristic polynomial of the matrix of T with respect to a basis, and we have seen that similar matrices will have the same characteristic polynomial, and hence there will be no dependency on the basis. So we will use all this knowledge to get hold of a matrix of T with respect to a given basis. We will get hold of the characteristic polynomial, and then we will see whether it is diagonalizable or not. Okay, so that's the strategy. So let's fix a basis. So let beta equal to 1x square be a basis, an ordered basis. So let me write it that way, an ordered basis of P2 of R. Now let's calculate what is T beta, the matrix of T with respect to beta. Then T beta, let's find. Then let us calculate T beta. So to do that, let's see what is the column representation of each of the vectors in beta. So notice that T of 1 by definition is the 0 polynomial, because the derivative and the second derivative of any constant for that matter is 0. How about T of x? T of x will be x prime is 1 plus x double prime is 0. So this is going to be 1. And T of x square will be 2x, which is p prime, plus p double prime is So this is exactly what our polynomials look like. And from this, we can directly write the polynomial of t with respect to beta then is 0, 0, 0 in the first column, because 0 is represented in this manner. How about 1? 1 is represented as 1 times 1 plus 0 times x plus 0 times x square. And 2x plus 2 is represented by 2 times 1 plus 2 times x plus 0 times x square. Good. So what is the characteristic polynomial? The characteristic polynomial of t beta is the determinant. This is equal to det of t beta minus lambda I. So notice that P2 of R is a dimension 3 vector space, so this is I3. So this matrix is a 3 cross 3 identity matrix, and we'll be able to write this easily as the determinant of minus of lambda 0, 0, 1 minus of lambda 0, 2, 2 minus of lambda, which is nothing but minus of lambda to the power 3. And therefore, the roots of the characteristic polynomial is just 0. The eigenvalues, which are the roots of the characteristic polynomial, is just 0. The eigenvalue of t is the scalar 0. 0 is the only eigenvalue of t. But then if we want a basis consisting of eigenvectors, the eigenvectors should have some eigenvalue, and we now know that 0 is the only eigenvalue. And therefore, if the eigenspace of 0 is not the entire vector space, then t is not diagonalizable. So notice that since t is not the 0 linear transformation, the eigenspace corresponding to lambda naught is strictly contained in P2 of R, where lambda naught is equal to 0. Because if E lambda naught is equal to P2 of R for lambda naught equal to 0, that would mean that t kills every vector in P2 of R, but that's certainly not the case, because for example t of x square was 2x plus 2, which is not 0. So hence we will not be able to get hold of a basis consisting of just eigenvectors. Hence there does not exist a basis consisting of eigenvectors of t. Hence t is not diagonalizable. Okay, so that solves the first part. How about the second one? The second one dealt with the following linear transformation: 2. T of ax square plus bx plus c. This was defined as cx square plus bx plus a. So in particular, let's again beta be the same standard basis that we had considered earlier. T of 1 is just equal to 0x square plus 0x plus 1, which turns out to be x square here. Similarly, t of x is equal to x, and t of x square, ax square plus bx plus c becomes cx square plus bx plus a. So this is just equal to 1, right? So hence, what would be the matrix of t with respect to beta? That will just turn out to be equal to 0, 0, 1. T of 1 is 0 times 1 plus 0 times x plus 1 times x square. 0, 1, 0 in the case of t of x, and t of x square is 1, 0, 0. Well, that's good, because now we'll be able to look at the characteristic polynomial. Characteristic polynomial is the determinant of the matrix t beta beta minus lambda I, again 3 here, which is just going to be equal to minus lambda 0, 1, 0, 1 minus lambda 0, 1, 0 minus lambda, be determinant of this matrix. The determinant of this matrix is quite straightforward. This is equal to minus of lambda into minus of lambda, which is lambda square times 1 minus lambda plus 1 times minus of 1 minus lambda. So minus of 1 minus lambda. This is basically lambda square minus 1 into 1 minus lambda. So if you look at the roots of the characteristic polynomial, we get the eigenvalues. Hence, the eigenvalues of t are lambda 1 is equal to 1 and lambda 2 equal to minus 1. Why? Because this is lambda, this is just minus of lambda plus 1 into lambda minus 1 the whole square. So there are two roots and they are going to be the eigenvalues. So to check whether t is diagonalizable or not, we have to get hold of, if at all t is diagonalizable, then there exists a basis. There exists a basis of R3 consisting, here in this case, sorry, P2 of R consisting of eigenvectors. So let's see if whether we will be able to do that. So let's focus on lambda 1 equal to 1 and let's get hold of the eigenvectors corresponding to lambda 1 equal to 1. What will be the eigenvectors corresponding to lambda 1 equal to 1? It will be the set of all ax square plus bx plus c such that t of ax square plus bx plus c is equal to ax square plus bx plus c. And if this is the case, then what do we have? Then we have this is equal to, by definition, this is equal to, so let me write it like this. Ax square plus bx plus c will be equal to t of ax square plus bx plus c if ax square plus bx plus c is an eigen vector corresponding to the eigenvalue 1. But we know that t of ax square plus bx plus c is cx square plus bx plus a. And by equating coefficients, this gives that eigenvectors. So this gives that a is equal to c. So hence, if ax square plus bx plus c is an eigenvector, then a is equal to c. If a is equal to c, also if a is equal to c, then what will happen? T of ax square plus bx plus a will just be equal to ax square plus bx plus a, which gives that E lambda 1 is just the set of the eigenspace corresponding to lambda 1 is the set of all ax square plus bx plus c such that a is equal to c. Well, let me just leave it for you to check that. This is just, let me write it like this, a times x square plus 1 plus bx, where a comma b belongs to R. So we know exactly what the spanning set, what is the basis of this, which is equal to the span of 1 plus x square comma x. So this is going to be the eigenspace corresponding to lambda 1. How about lambda 2? So let me just see if minus of ax square plus bx plus c, that is what is the eigens. Oh, I wrote it. It doesn't matter. Let me just be careful. This is ax square plus bx plus c, but this is equal to cx square plus bx plus a. So if the polynomial ax square plus bx plus c belongs to the eigenspace corresponding to minus 1, this would imply that a is equal to minus c and b is equal to minus b, 2b equal to 0, which implies that b is equal to 0. So yeah, 2b equal to 0. That is what we will be able to conclude. So in along the same line of arguments, e lambda 2 will be just equal to
the span of, this is just going to be ax square minus 1. So a times x square minus 1, where a belongs to R. So hence, we have three vectors. 1 plus x square, x, and x square minus 1 are eigenvectors of T. And if you notice, if you go back and check, this is going to be a linearly independent set. What can we say about a linearly independent set of size 3 in a vector space of dimension 3? That has to be a spanning set as well. So this implies that, let's call it beta. Beta is a basis of P2 of R. So I'll leave the check for the fact that beta is linearly independent as an exercise for you, and that will help us conclude that beta is a basis, which implies that T is diagonalizable.
So T of P of X is equal to P prime, or maybe not, P of 0 plus P of 1 times X plus X square. Okay, let's see what is T of 1. T of 1 is just 1 of 0 is 1. P of 1, again, it doesn't matter, it's 1 times X plus X square. So this is going to be 1 plus X square. How about T of X? X of 0 is just 0, and P of 1 in this case will be, again, X is 1 times X plus X square. So just write it as X plus X square. How about T of X square? That will also be X plus X square, as you can check. So this is now going to be an interesting matrix. T beta beta is just 1 1 1 0 1 1 and 0 1 1. Okay, so what will be the characteristic polynomial? This will be the determinant of, I'll just skip steps slowly. This is just going to be 1 1 minus lambda 0, not 0, it's 1 1 1 1 minus lambda, which is equal to 1 minus lambda into 1 minus lambda the whole square minus 1, which is equal to 1 minus lambda times lambda square plus 2 lambda plus 1 minus 1, which is lambda square minus 2 lambda, which is equal to lambda times 1 minus lambda into lambda minus 2. So what are the roots of the characteristic polynomial? Hence, the eigenvalues, which are the roots of the characteristic polynomial of T, are 0, 1 and 2. So notice that there are three distinct eigenvalues of T, and the dimension of P2 of R is also 3. So I will not even bother calculating or getting hold of the eigenvectors. By invoking one of the theorems we have proved in the lectures, since T has three distinct eigenvalues, we have that T is diagonalizable. So the first example was not diagonalizable in the problem that was given. However, if we tweak the problem, change the vector space to P2 of C, which is a vector space over C, and define the linear operator T similarly, then it turns out to be diagonalizable. And the third problem is a problem which indeed is diagonalizable. It is a linear operator which indeed is diagonalizable. So with that, we complete the first problem. Okay, the next problem. The next problem discusses the relationship between T and T inverse, about whether what can we say about the eigenspaces and eigenvalues of T inverse when we know about the eigenvalues and eigenspaces of T. Further, whether we can conclude anything about diagonalizability of T inverse when the diagonalizability of T is known. So let me write down the statement of the problem. So let T be an invertible linear operator on a vector space V. So let me impose a finite dimensionality here, finite dimensional and suppose that lambda is an eigenvalue of T, and prove that lambda inverse is also an eigenvalue of T. So let me write it like this, prove that the eigenspace of T corresponding to lambda, so suppose lambda is an eigenvalue of T, and suppose the eigenspace of T corresponding to lambda is known, then the problem is to prove that the same subspace will be an eigenspace of T inverse corresponding to lambda inverse is the same as the eigenspace of T inverse corresponding to lambda inverse. Furthermore, prove that if T is diagonalizable, then T inverse is. Well, if we solve the first part of this problem, then the second part easily follows. So is T inverse. Okay, so it's a proof problem. So let me write it down as proof. So the first observation is to see that lambda inverse is indeed an eigenvalue of T inverse. So let lambda be an eigenvalue. Okay, so very careful, we should be very careful about it. Before we even begin, notice that T is an invertible linear transformation. What can we say about invertible linear transformation? We can say that the invertible linear transformations will not have any element in the null space, and therefore 0 cannot be its eigenvalue. Since T is not invertible, 0 is not, or is invertible rather, is invertible, 0 is not an eigenvalue of T. And that tells us that if lambda is an eigenvalue, we can talk about 1 by lambda, right? So let lambda be an eigenvalue of T. And the moment there is a lambda which is an eigenvalue, let V be some non-zero vector such that Tv is equal to lambda V. And V be a non-zero vector such that Tv is equal to lambda V. So what do we know about T inverse? T inverse is the inverse of T, right? So T inverse T is the identity map, and T inverse TV, the same eigenvector that we just took, that is IV, which is equal to V. But we know what TV is. TV is lambda V, right? That means T inverse of lambda V is equal to V. That implies T inverse is a linear map, lambda can be taken out, and it can also be inverted. I'll just put everything together and say that this is 1 by lambda times V. That means that 1 by lambda is an eigenvalue of T, and V is an eigenvector of T inverse. 1 by lambda is an eigenvalue of T inverse, and V is also an eigenvector of T inverse. So what we have proved here just now is that if V is an eigenvector of T corresponding to lambda, then V is also an eigenvector of V inverse of T inverse corresponding to 1 by lambda. So let me just note that down. This implies V is an eigenvector of T inverse corresponding to lambda inverse. So that it's not that we have just shown that if lambda is an eigenvalue of T, 1 by lambda is an eigenvalue of T inverse. We have shown more. We have shown that V is also the eigenvector of t corresponding to lambda will also be the eigenvector of t inverse corresponding to 1 by lambda. So now I should be able to say this, the eigenspace, which hence eigenspace of t corresponding to lambda is contained in the eigenspace of t inverse corresponding to 1 by lambda. But then this is a symmetric argument. If we had started off with t inverse in place of t and t in place of t inverse, we would have got the other way, other side containment. Similarly, eigenspace of t inverse corresponding to 1 by lambda is contained in eigenspace of t corresponding to lambda, which implies that they are equal. The eigenspaces are equal. That's what we had set out to prove. But then there is a second part to the problem, if you recall. It's not that we were attempting to only prove that eigenspaces are the same. We also wanted to show that if t is diagonalizable, and so is t inverse. But that's quite straightforward, because if t is diagonalizable, then we have a basis consisting of eigenvectors of t. And we just showed that every eigenvector of t is also an eigenvector of t inverse. And therefore, the same basis will give you what we want. Since, let me just note that t is diagonalizable, there exists eigenvectors, there exists a basis beta equal to v1 to vn of eigenvectors of t. But these are also eigenvectors of t inverse. This implies that there exists a basis of t inverse consisting of eigenvectors. That's precisely what it means to say that a given linear operator is diagonalizable, which implies that t inverse is diagonalizable. So we have shown all the parts given in the second problem. The next problem is regarding the cyclic subgroup generator. So the next problem is regarding the t cyclic subspace generated by a vector in a vector space capital V. So let me write down the problem. So let V be a vector space and T be a linear operator. This is, I think, problem 3. Linear operator on V. Suppose W is the T cyclic subspace of V generated by some non-zero vector, by a non-zero vector V. Then prove that there exists a polynomial G such that G of T for every W in capital W, there exists a polynomial G such that G of T V is equal to W. So that is the problem. Prove that for every W in capital W, there exists a polynomial G of T such that G of T V is equal to W. So we have done some the techniques or the idea that will be used to prove this particular statement. So let me just show you the statement once more. We have already seen something similar once, but it's good to keep these kind of arguments in mind. So let's just go over what to do to get hold of some such G over here. So what is the definition of a T cyclic subspace generated by a vector? So let me give it as a proof this time. So W is the T cyclic subspace of V generated by V. That means that this is the span of the vectors V, TV, T square V, and so on, T cube V, and so on. What was T to the power KV? That is T acting on T acting, so T acting on V K times. So T of T of T of T of V, K times this is acting. That's what T to the power KV is. And W is the span of the vectors T, V, TV, T square V, T cube V, and so on. So notice that we have not imposed the requirement that V should be a finite dimensional vector space. That requirement is not there. So it is possible that W is infinite dimensional. Okay, so let W be in capital W. That means it is in the span of V, TV, and so on. So that means let A1 to AN be such that W is equal to A1T K1V plus A2T K2V plus ANT KNV. But this is the same as A1T K1V, sorry, A1 TK1 plus A2 TK2 plus AN TKN, this acting on V. So let's define G of T to be equal to A1 times T to the power K1 plus A2 times T to the power K2 plus AN times T to the power Kn. When then all the conditions in the hypothesis are satisfied by G, and yes, there exists a polynomial G such that G of TV is equal to W. So let me just add a small portion to this. Moreover, if W is finite dimensional, then G can be picked. That's also actually visible from what we have just done, such that degree of G is less than or equal to the dimension of W. Okay, so let's see what this means. What this means is the following. So suppose dimension of W is say M. So my first claim is that T to the power K V belongs to the span of V T. Let me put it as M plus 1 so that I don't have to worry about keeping this M minus 1 at the top. I can now write safely TMV for all. So this is my first claim. For all K greater than or equal to M plus 1. So this is my first claim. So the proof, we have already seen this proof in one of the lectures, so I will not go into it. It is a proof by induction. You check that for K equal to M plus 1, this is getting satisfied, and then by the strong induction hypothesis, you can write that any T to the power KV is in the span of this. But the moment this happens, what this implies is that W is the span of V TV up to T to the power MV, because any T to the power KV for K greater than M will be in the span already. So the span of V, TV, T square V, and so on will be in this, exactly equal to this in fact. But that implies that W is in the span of all these vectors. which implies that there exists A1 to, this case, let me now use B1 so that there is no confusion. B1 to Bm such that W is equal to V, let me use B0 to B0 V plus B1 TV plus up to BMTV, BMTMV. Now define G of t to be equal to B0 plus B1t plus up to Bmt to the power m. Then clearly G of t has degree less than or equal to m, and G of t v is equal to W. So if W is finite dimensional, we can even pick G to satisfy some nice properties. In the next problem, we will discuss an application of the Cayley-Hamilton theorem. So let me write down the problem for you. So this is going to be problem 4. So let A be an n cross n matrix. So let's write it as M and R. Let A be an n cross n matrix with real entries. Then prove that dimension of the vector subspace W of Mn of R is less than or equal to n, where W is the span of the vectors I, A square, and so on. This is the span of the collection I, A square, and so on. And then we will be able to say that the dimension of W is less than or equal to n. Well, that's quite straightforward. So let's see. If we have the power of the Cayley-Hamilton theorem, then this is quite nice. So if you have the power of the Cayley-Hamilton theorem, this is quite straightforward. Notice that an n cross n matrix can be thought of as a linear transformation from Rn to itself. Since A belongs to M n of R, consider LA from Rn to itself, which is an n-dimensional space. Rn is an n-dimensional space. This implies that the characteristic polynomial of LA, which is the characteristic polynomial of A, has degree less than or exactly, in fact, equal to the dimension of Rn, which is equal to n. That is the degree of the characteristic polynomial, dimension of V. So that means f of lambda, which is the characteristic polynomial of A, has degree n. So let's see. F of lambda is equal to minus 1 to the power lambda minus 1 to the power n times lambda to the power n plus so on. So the lower order terms plus A0, which will turn out to be the determinant. Anyway, we are not interested in that, but nevertheless, by the Cayley-Hamilton theorem, the matrix A satisfies this polynomial. The Cayley-Hamilton theorem we have shown a version of the Cayley-Hamilton theorem for the linear operators, but it's going to be the same. So it's going to imply the same. F of LA is equal to the 0 vector. It's identically equal to 0. That's what it means. But what is the meaning of f of LA? This implies that, well, equal to 0 implies that minus 1 to the power n times LA acting on itself n times plus so on up to A0 I is the 0 linear operator. That's what it means. And by going down to the basis, this implies that minus 1 to the power n times A to the power n plus so on. Let me just write the second term. A n minus 1 a to the power n minus 1 plus a0 I is the 0 vector. So this implies that a to the power n belongs to the span of I, a square up to a to the power n minus 1. But that implies that a to the power k belongs to the span of I, a square up to a to the power n minus 1 for all k greater than or equal to n, which implies that W is contained in the span of I, a square up to a to the power n minus 1. But what is W? W is the span of I, a square and so on, and therefore the right hand side in particular is contained in W. So this implies, hence, by this observation and the fact that span of I, a square up to a to the power n minus 1 is contained in W, we get W is equal to the span of I, a square up to a to the power n minus 1. So what do we have? We now have a spanning set which has size n. And what can we say about the dimension? The dimension will always be less than or equal to the size of a spanning set, since W has a spanning set of size n. We can conclude that dimension of W is less than or equal to n, and hence we have proved the result. In the next problem, we will discuss some properties in an inner product space. So this is going to be problem 5. So let V be an inner product space. So let capital V be an inner product space and well u comma v be vectors in capital V. Then the inner product of u comma v, then prove that, this is what we have to show, prove that inner product of u comma v is equal to 0 if and only if norm of u is less than or equal to the norm of u plus a times v for all a in F. So notice that I am using the word F. So this is true even in the case when V is a complex inner product space. So what the statement tells us is that if you have that u and v are orthogonal, then norm of u is less than or equal to norm of u plus av for all a in F. And further, if norm of u is less than or equal to norm of u plus av for all a in F, then u and v are orthogonal to each other. Both sides are being demanded. So let's prove the result. One side should be easy. So let's see. If inner product of u comma v is equal to 0, then what is it that we know about the norm of u plus av, the whole square? We know that by Pythagoras theorem, this is equal to, well I was using the word norm, but what I mean is length. So this is going to be length of u square plus mod of a times length of v square. Notice that this is a positive quantity. The mod of a times length of v square is a positive quantity. So this implies that u square is less than or equal to the length of u square is less than or equal to the length of u plus av the whole square. By taking square root, the length of u is less than or equal to length of u plus av. Now this is true for all a in F, and therefore this is also true for all a in F. This is also true for all a in F. So we have proved one side of the result, which was easy. We have shown that if u comma v, the inner product is 0, if u and v are orthogonal, then the inequality is satisfied. Let's assume, okay, so the conversely, let length of u be less than or equal to length of u plus AV for all A in F. So let's now try and conclude that u plus AV is u and v are orthogonal. Okay, so what is the length of u plus AV the whole square? This is just the inner product of u plus AV with u plus AV, and that is equal to the length of u square plus A times v comma u plus A bar times u comma v plus mod A square times the length of v square. So let's look at what is the length of u plus AV square minus the length of u square. That is equal to A times v comma u. So let me just write this as 2 times the real part of A bar times u comma v. Why is that the case? Because A times the inner product of v plus u when added to its conjugate, that will give you 2 times the real part of one of the two. Well, A times the inner product of v comma u will have the same real part as the complex number A bar times u comma v. So I'm writing down everything under the assumption that it is possible that our vector space is a complex inner product space. So then this makes sense. So plus mod A square times the length of v square. So this is to be satisfied by every scalar A. So let's now carefully pick our scalar. So we want the quantity to the left to be greater than 0. This, the whole square minus this, is greater than or equal to 0 for all A in F implies, so let's write down the right hand side, 2 times the real part of A bar times inner product of u comma v plus mod A square times the length of v square is greater than 0. Just 1 second. So let's carefully pick A. So pick A to be equal to, okay, so let's see, if v is equal to 0, then there is nothing to prove, right? Then u comma v will have inner product equal to 0 and we will be done, right? So the case when v is equal to 0, the solution is clear. The proof follows. So we may assume without laws of generality that v is not equal to 0. So when v is not equal to 0, let's pick a very special A. This is after all satisfied, the star is satisfied for all A in F. So let's pick A to be equal to the inner product of u with v by the length of v square. Let's pick this particular scalar and let's see what happens. Then star, then LHS of star will be 2 times real part of A bar will be inner product of u comma v bar by the length of v is a real number, so this is just a real number, times the inner product of u comma v. And how about mod A square? Mod A square will be inner product of u comma v the whole square by norm v square, length v square, the whole square. So this is going to be length v to the power 4 times length of v square, which is just going to be equal to 2 times the real part of absolute value of u comma v the whole square by length of v square. Why would it be the absolute value? Should check that if z is equal to a plus ib, z bar is equal to a minus ib, and z bar will be just a square plus b square, which is the square of the absolute value of z. So this is exactly what we will be getting. Plus, after cancellations, the next term will just be equal to absolute value of inner product of uv the whole square by the length of v square. But notice that we are looking at the real part of a real number, so that has to be the number itself. So this is equal to 2 times, let me be a little careful here, so let's do one thing. This will not work, so what we'll do is we'll change the sign a bit. Let's put a to be minus of this number. That is when the fun begins. Then this will be minus of this, then this is going to be 2 times minus of this, which is 2 times minus of this, which is minus of 2 times the inner product, absolute value of inner product of u comma v square by length of v square plus absolute value of u comma v the whole square by the length of v square. I'll just explain what was going on. If we had picked a the way we had picked earlier, we would have just ended up with some number which is greater than or equal to 0, and we wouldn't have been able to conclude much. But what we have done is, by changing the sign, now here this is just going to be equal to minus of 2 times the absolute value of the inner product of u comma v by the length of v square. And what do we know? Just go back to star. Star here tells us that quantity should be necessarily greater than 0, right? Star by star minus of 2 times absolute value of u comma v by the length of v square should be greater than 0. We can safely multiply by length of v square, which is a positive quantity, and conclude that, in fact, we can conclude that the absolute value of u comma v is less than, that should be greater than or equal to 0. This should be less than or equal to 0. I am sorry, this is greater than or equal to 0. By multiplying by minus 1, we get this is less than or equal to 0. But absolute value of a complex number, this cannot be negative. This implies that the absolute value of u comma v is equal to 0. But how can the absolute value be equal? If it is equal if and only if the complex number itself is equal to 0. And that's precisely what we had set out to. So let's just quickly go back to see what we have done. What we have done is that we wrote down the expression for the length of u plus a v square, and from there we managed to get hold of an equality of this sort, and we know that length of u is less than or equal to the length of u plus av. In particular, length of u square is less than or equal to the length of u plus av the whole square, and therefore the length of u plus av the whole square minus the length of u square is greater than or equal to 0. And that's precisely what was used here, and we concluded that RHS will also hence be equal to be greater than or equal to 0. So I'll just make a slight correction here. I missed a greater than or equal to. This should be a greater than or equal to from the above, and that's precisely. And then what did we do? We picked our a very carefully when v is not equal to 0. We picked our a to be something like this, and then with that carefully chosen a, we ended up with the absolute value of the inner product of u comma v being equal to 0, which forced them to be orthogonal to each other. Okay, that solves the fifth problem. The next problem is an application of the celebrated Cauchy-Schwarz inequality. As you might know, as I have told you earlier, Cauchy-Schwarz inequality is one of the most important theorems in the field, and its power is immense. So let's look at one problem to slightly indicate that it is actually quite a powerful theorem. So prove that summation aj bj the whole square is less than, so this is j equal to 1 to n, this is less than or equal to summation jaj square, where j is taken from 1 to n, times summation bj square by j, where j is equal to 1 to n. This is true for all ai comma bi in R, where I is equal to 1 to n. So at first glance, it might not look like Cauchy-Schwarz inequality might come into the picture. So this is just some inequality involving a few real numbers and the squares. But we will very soon we will convert this problem into a problem which involves the relevant vector spaces as is to be guessed in Rn. We will use the standard inner product and the Cauchy-Schwarz inequality in a smart way. So let's see how it can be done. So this is a proof problem. So let me give a proof. So consider Rn with the standard inner product. And let's pick a1 to an and b1 to bn arbitrarily. So let a1 to an comma b1 to bn be vectors in Rn. So let them be n tuples. Now let's try and recall what Cauchy-Schwarz inequality says. By Cauchy-Schwarz inequality, we have the inner product of a1 to an and absolute value of the inner product of a1 to an comma b1 to bn. This inner product, this is less than or equal to the length of the vector a1 to an times the length of the vector b1 to bn. This is precisely what the Cauchy-Schwarz inequality says. But we'll do a slight tweaking here. So let's do one thing. Let's now define ai prime to be equal to I times ai. Similarly, or maybe not, maybe square root of I times ai. Similarly, bi be equal to bi by square root of I. So we will define now ai prime and bi prime in this manner. So apply Cauchy-Schwarz to these vectors. We will not apply Cauchy-Schwarz to our a1 to an and b1 to bn. We will apply it to a1 prime to, let me write it down, applying, let me shorten it to cs for Cauchy-Schwarz, to a1 prime up to an prime and b1 prime up to bn prime. What will be the LHS? LHS will be the absolute value of the inner product of, well, write it down, y b in a hurry, this and b1 prime to bn prime. This is less than or equal to the absolute value of, no, the length of a1 prime to n prime times the length of b1 prime to bn prime. What is the LHS here? LHS is just a1 prime b1 prime plus a2 prime b2 prime plus up to an prime bn prime. absolute value of this. This is less than or equal to, so what is it that we have to show? We have to show that this square is less than or equal to this. So in particular, this square is also less than, all these are positive quantities. So Cauchy-Schwarz will in particular give us this. So the left hand side, this square will be equal to, what will be the length of a1, a2 up to an, a1 prime, a2 prime up to n prime in this, with respect to this inner product. It will just be equal to the sum of a1 prime square plus up to an prime square. That will be the length of a1 prime up to n prime, and this will be b1 prime square plus up to bn prime square. Now let's go back to see what our ai primes and bi primes were. Ai prime was square root of I times ai, and bi prime was bi by square root of I. So ai prime times bi prime is just ai times bi. So that's what we will use to write the left hand side here. And I can throw out the absolute value because the square will anyway be a positive number. So this is just going to be a1 b1 plus a2 b2 plus up to an bn the whole square. This is equal to this, by the way. And what about this? This is just going to be equal to 1 times a1 the whole square, no, square root of 1 times, which is 1, plus square root of 2 times a2 the whole square plus square root of n times an the whole square times, similarly, b1 by 1, which is b1 square plus, so let me just write it down here, by 1 plus b2 square by 2 and so on, plus bn square by square root of n the whole square, which is n. So this is less than or equal to, the RHS is now just summation, well, let me write it as j aj square times summation bj by bj square by j, where j goes from 1 to n. And that's precisely what we had set out to prove. So by picking our vectors very carefully, Cauchy-Schwarz inequality is giving us some remarkable inequality that we have seen here. So the final problem in this problem session involves an identity that is true in a complex inner product space. So let's look at what the problem is. Problem 7. So let V be a complex inner product space. Prove that the inner product of u comma v, this is equal to the length of u plus v the whole square minus the length of u minus v the whole square plus I times the length of u plus I times v the whole square minus the length of u minus I times v the whole square whole divided by 4. Okay, let's see what this is. So let's look at what the RHS is going to behave like. So let's look at what is the length of u plus v the whole square minus the length of u minus v the whole square plus I times the length of u plus iv the whole square minus, this is just going to be a huge computational problem involving I and uv and I, but nevertheless it's beneficial to look at it because it will help us get familiarized to using inner products. So let's see, this will be, what is the length of u plus v the whole square? That is the inner product of u plus v with itself. And how about the next term? This is u minus v with itself plus I times the inner product of u plus iv with itself minus u minus iv, inner product of that with u minus iv. Now let's expand it out and let's keep track of all the properties of the inner product that we have seen. This is just going to be equal to, I'll be a little quick here to write it down, u, so I'll just write it down. The first term will be length of u the whole square plus length of v the whole square plus inner product of u comma v plus inner product of v comma u. That is the first term, minus what will be the second term? That will be the length of u square plus the length of v square, minus 1 minus 1, 2 minus 1s will cancel off, and minus the inner product of u comma v minus the inner product of v comma u. So that is the first term. How about the second term? I times, let me be a little careful here, I'll write down things explicitly and then we will write down the final expression. This is going to be u comma u plus u comma iv, which is going to be I bar times u comma v plus iv comma u, inner product of iv comma u, which is I times inner product of v comma u, plus the inner product of iv comma iv, which is mod of I square. So let me put it this way, I bar times v comma v. That will be the first term. That will be the first term, minus, how about the second term? Second term will be very similar, u comma u, now minus of I times v comma u minus of I bar times u comma v plus I bar times v comma v. The second term is where all the I had to be taken care of carefully. So the first term is easy. First term will u square, length of u square and length of v square cancels off. This is just going to be 2 times the inner product of u comma v plus the inner product of v comma u. And now let's focus on the second term. The second term will be plus I times the length of u square plus I bar times, so I bar is just going to be minus I, you should check that, minus of I times u comma v plus I times v comma u plus I bar is absolute value of I square, or you can check directly that it is minus of I square, which is 1. So this is just going to be plus length of v square. So that is this first term, and then the second term is again similarly length of u square minus I times v comma, there is a bracket here. This just turns out to be a lot of bookkeeping, but so this will cancel off and this will be plus I times u comma v. Nevertheless, let me do it. And this is going to be, what is uv plus vu? Vu is uv bar, right? So this is equal to u comma v conjugate. And what is a plus ib plus a minus ib? It's 2a, which is 2 times real part, right? So this is equal to 2 times the real part of the inner product u comma v. And there is a 2 outside, so 2 times 2 of this. It's good. And how about this? This is I times, the situation is quite similar. This is just going to be equal to 2 times, maybe I can take I also out, and there will be a inner product of v comma u minus u comma v. Okay, so that is good. Notice that this is just u comma v bar, the conjugate of v comma u. And what will happen if you subtract the conjugate from something? What you get is, so let me write it down, this is 4 times real part of the inner product of u comma v plus, so there is an I, which is I square, times 2 into the imaginary part of v comma, or maybe I should put it this way. Yeah, let's see. We'll come to it in a minute. So this is equal to, there is a 2. And this is, why is that the case? Because this is, say, if this is a plus ib and this is a minus ib, should do the subtraction and see that a plus ib minus a minus ib is, oh, there is an I. There is an I. So we should be careful. So 2I times the imaginary part of inner product of v comma u. So the answer when you subtract will be 2ib, which is 2 times I into imaginary part of that. So that's what I have written here. So this is again 2 to 4 is there, 4 times the real part of u comma v minus, so 4 has been taken out, I times imaginary part of v comma u. But v comma u, inner product of v comma u is, let me just rewrite this, this is inner product of u comma v bar. But when you look at the imaginary part of z and imaginary part of z bar, what do you have? Imaginary part of z bar is the minus of the imaginary part of z. So this is just going to be equal to 4 times real part of the inner product of u comma v plus I times the imaginary part of u comma v. But that is the imaginary real part of z plus I times the imaginary part of z, which is actually equal to 4 times the inner product of u comma v, which is what we had set out to prove. So I would request you, if you are not familiar with the operations of complex numbers, I will request you to go through these steps very carefully. And I ran over the reasoning without bothering to emphasize, and but all of them are quite straightforward. You should, however, sit back and check that all these, what are the properties of the complex numbers that are being used to conclude various things here. All right, so let me stop here.